Okay, so last lesson for the chapter, 3-5, limits at infinity, and we jump up to 3-5 just to keep all the limits together. So we'll warm up, graph the function 1 over x, and write an equation for the vertical and horizontal asymptotes. And we'll go over this in class. Again, no calculator, please. All right, definition of a horizontal asymptote. If the limit as x approaches negative infinity of a function equals L, or the limit as x approaches positive infinity of a function is some number L, then y is equal to L is a horizontal asymptote. A graph can have at most 2 horizontal asymptotes, okay? There's no limit on vertical asymptotes. Okay, so let's talk about the difference here between the last lesson and this one. If you have a vertical asymptote, then we know the one-sided limits from the left, or the limit of a function from the right, approach positive or negative infinity. When your answer is positive or negative infinity, this is known as an infinite limit. Okay, your answer is infinite. If you look at the title of this lesson, it's limits at infinity. Now we're looking at as x gets infinitely larger. So this is your limit at infinity. Okay, your limit at infinity will describe if they exist horizontal asymptotes. If your answer is an infinite limit, it will describe for you a vertical asymptote on the graph of the function. Horizontal asymptotes are not discontinuities. Okay, not a discontinuity. Vertical asymptotes, we know, do come from a discontinuity on the function. Okay, and we'll look at some examples, and hopefully the difference between those two will become very apparent. All right, so recall end behavior. So you would have studied end behavior last year. And it's exactly that. What's happening at the ends of the function? In order to determine what the end behavior is, we look as the limit as x approaches positive infinity. So as x is getting bigger and bigger and bigger and bigger, what are my y values approaching? So in this particular function, my y values are approaching infinity. End behavior is always 2 limit statements. Limit as x approaches infinity, limit as x approaches negative infinity. As x gets smaller and smaller and smaller, what are my y values doing? They're getting infinitely smaller as well. Because these limits do not exist, there's no horizontal asymptote on the graph of the function, which is apparent just from the looking at this simple sketch. Okay, now what if I look at a graph like this? And I ask you to describe the end behavior of the function. As x gets infinitely larger, what are the y values of my function doing? They're approaching 2. They're appearing to level out at 2. As x gets infinitely smaller, so as x approaches negative infinity, what are my y values doing? They're leveling off or approaching negative 2. Because these limits exist, each one individually tells us the existence of a horizontal asymptote. So we can have 2 different horizontal asymptotes for the graph of one function. Okay, very important theorem that we'll continue to use. If R is a positive rational number and C is any real number, then the limit as x approaches infinity of a function in this exact form will always be 0. Likewise, limit as x approaches negative infinity, if the same conditions are met, will be positive 0, or excuse me, will be 0 as well. Think about what this theorem says. Okay? C is any real number. R is any positive rational number. All right, so we can even have a fifth. As x gets bigger and bigger and bigger and bigger, my numerator, or excuse me, my denominator is just going to grow. So 2 divided by a huge number is just going to be smaller and smaller and smaller. Okay? Even down here, and I can approach negative infinity on this graph. So r just has to be a positive rational number because we have to keep the variable in the denominator. If x gets infinitely smaller, it's just going to get smaller and smaller and smaller. A number divided by that really, really negative number is going to approach 0 as well. So we'll use this theorem early and often. Okay, to find a limit at infinity, which you would have done last year, divide each term of both the numerator and denominator by the degree of the denominator, and then evaluate the limit of each term. So when I say, sorry about that, when I say degree, just recall that that means the highest exponent from the bottom. Okay. I have a rational function, therefore I could potentially have a horizontal asymptote. So we look at the limit as x approaches infinity first. So the degree of the denominator, the highest exponent is just x. And I'm only going to use x. You could incorporate the coefficient, but you do not need to. Right, so 4x plus 3 all divided by 2x minus 1. And I'm going to divide each term by x. Okay, so after you divide each term, we'll simplify the function. So I get 4 plus 3 over x divided by 2 minus 1 over x. Now evaluate the limit of each simplified term. Well, the limit as x approaches anything, whether a number or infinity, of a value is itself. So the 4 over 2 will remain from the bottom. From the theorem on the previous slide, this limit approaches 0, as does the limit of 1 over x. So the limit of this function, the limit as x approaches infinity, would be positive 2. Now, end behavior, you always have to look at both cases, positive and negative infinity. And I'm going to use the simplified function. Okay, so I get the same ratio of 4 over 2. And these will approach 0 as well, because the theorem said it doesn't matter if you're approaching positive or negative infinity. Because the limits at infinity exist, what can we conclude? There's a horizontal asymptote at the line y is equal to 2. Okay, f of x equals 2x squared over x plus 1. Limit as x approaches infinity. So my degree term on my denominator is x. So I'm going to take each term of the function and divide it by x. Limit as x approaches infinity. 2x squared over x would reduce to 2x. And I have 1 over 1 plus x. All right, now when I attempt to find the limit of each individual term, all right, this will approach 0 in the bottom. The 1 stays put. And now think about what's happening in the numerator. You have 2, and I know this doesn't make sense mathematically, but your x values are getting bigger and bigger and bigger. So what's an infinitely large number times 2? Another infinitely large number. So what do we say about the limit as x approaches infinity? It does not exist. Now let's check the case as x approaches negative infinity. So again, we can use a simplified form. My denominator will remain 1. And now think about what x is doing. X is getting infinitely smaller. So if I take that number and multiply it by 2, my y values are just going to get infinitely smaller as well. What does this tell me about the limit? The limit does not exist. And then what can I conclude? There's no horizontal asymptotes on the graph of the function. Alright, let's look at f of x equals 4 plus 3 over x squared plus 2. So end behavior, limit as x approaches infinity. All right, now this whole function is 4 plus this rational function. So I'm going to break it up. Limit as x approaches infinity of 4 plus the limit as x approaches infinity. Degree term is x squared. So I'm going to take 3 divided by x squared over x squared, plus 2 over x squared. So I have the limit as x approaches infinity of 4 plus 3 over x squared all over 1 plus 2 over x squared. So now when I find the limit of each individual piece, this limit approaches 0 according to my theorem, as does the one on the bottom. So all I'm left with is 4 plus 0, which is 4. Just because I'm running out of space on the slide. If I made this a negative infinity, these limits would still approach 0. So my limit as x approaches negative infinity would be 4 as well. So what can we conclude? There's a horizontal asymptote at the line y is equal to 4. Okay, the shortcut, the nice simple shortcuts for finding a limit at infinity only. So a rational function will fall into one of 3 categories. We describe it as top-heavy, equal, or bottom-heavy. Top-heavy, degree of the numerator is greater than the degree of the denominator. Equal, degree of the numerator is the same as the degree of the denominator. Or bottom-heavy, the degree of the numerator is less than the degree of the denominator. So when you are approaching a limit at infinity only, these shortcuts can be used. If the function is top-heavy, the limit at infinity will automatically not exist. If the function is what we consider to be equal, the limit at infinity will be just the ratio of the lead coefficients. If the function is bottom-heavy, then the limit at infinity will always be 0. So let's look at what these mean. Use the shortcuts to find each limit. Limit as x approaches infinity, x squared plus 2 over x cubed minus 1. Compare the degree of the numerator with the degree of the denominator. It's bottom heavy. The degree of the denominator is bigger than that of the numerator, so that limit will approach 0. Done. You can use the division in order to find the same answer, all right, the longer method that we just did, but you are not required to. Limit as x approaches negative infinity of 3 minus 2x all over 3x minus 1. The coefficient to the degree term in the numerator is negative 2, so don't lose that negative 2. 3x in the bottom. This is what an equal function would look like. Degree of the numerator, degree of the denominator are the same. So what's the limit? Just the ratio of the lead coefficients, negative 2/3. Limit as x approaches infinity of 3 minus 2x squared all over 3x minus 1. Degree of the term of the numerator, degree term of the denominator. It's top heavy. Degree of the numerator is bigger than the degree of the denominator, so the limit does not exist. What do these tell us graphically? Limit at infinity exists. There's a horizontal asymptote at the line y is equal to 0. Limit at infinity exists. This tells us that there's a horizontal asymptote at the line y is equal to negative 2/3. And lastly, if the limit does not exist, what does this tell us? Graphically, there's no horizontal asymptote. All right, we'll continue with this tomorrow.